closet.
Cool.
So we have that other room. Few people are joining from that room, like you can see probably. Yeah, you see that other people joining. Some, all of you settled, or if someone is standing, you can actually go to that other room. Is it okay?
We made it a little bit more cozy. If we'll keep the door open, our door open. It becomes too warm. Absolutely, yes. Oh, okay, very nice. Looking forward.
Hi, folks. Thank you for attending. My name's Kainwan, and I'll start my presentation. Sorry, it's a little awkward. The screen is there. You don't have to look at me. Okay. Yeah. So, guys, I've been in the industry a pretty long while, and I've had the opportunity to write some books. Happy to say that it's in the official Kernel docs, 3 of my books. And here they are. And in fact, I'm working on the next one. Okay, this has become a habit. And I'm working on a driver's book, but it'll take time. I will do my business pitch as well, forgive me. I run online training sessions as well as corporate training sessions. And I've been doing this for a very long time, especially the corporate ones. And interestingly, with AI being everything that it is, we are also launching AI-based courses. It will come up soon. I will be announcing on my site and on LinkedIn. You keep an eye out if you're interested. Guys, today, we don't have that much time, so I better start hurrying up because these topics are very large. So I want to talk about, perhaps common misconceptions. We know that we need to protect our shared data, but how do we do it? When do we do it? What technology do we use? Is there really a problem in our software code? How do we know that we need protection? So I will be addressing these things. And once we know we need protection and we do write code to implement protection, we tend to make mistakes. And we tend to have dangerous bugs like deadlock, which are very hard to predict and even debug, because these are all based on coincidental timing. Okay, so your test cases may never pick it up. If it could happen on the surface of Mars with the Pathfinder priority inversion, then it can happen in our projects, right? So it's not easy. The human brain is not great at synchronization. We tend to struggle with these things because complex interlocking scenarios are difficult to visualize what will happen. So instead of trying to do a computer science approach, I'm not great at that. I'm better at just doing what the tools we have, how to use them. Okay, so that is de facto what we'd be doing in the real world. I'll explain to whatever extent possible in this short time. There's a lot of primitives that we have for locking in the modern Linux kernel. Treat it as an overview, guys, because in half an hour, I can't go very much in depth, but then you can dive in further and you can learn more about them. It's first important to get a broad overview of, what is available and when do I use it. Then you can dive deep into the specifics. That is my thinking. Okay. And I'll close with a summary table of all of this stuff. So let's get going. As you can see, there are lots of primitives. Okay. And, the way the kernel evolves, it keeps increasing. Very broadly speaking, locking is what we use mostly. But of course, lock-free technology is very powerful, very performant, and it's becoming more and more important. Not that it's new. It's been there for a very long time. Okay. None of these things are really new. Okay. Why do I need to bother? What is the problem? Are we facing a problem? Yes, of course. We work with globals. In the Linux kernel, we have tens of thousands of them, and it's a monolithic design. So a global in the kernel is global to everyone in kernel space. We need to protect assets. We need to protect access to it. So the code path where you're accessing that global, it's called the critical section. But we don't jump to conclusions. What if the data we're accessing is truly read-only? Then there's no problem. Don't worry. Just go ahead and use it and nothing will go wrong. But if it isn't, then yeah, we have to start worrying about it. So guys, we have some conditions. Is this code path of mine a critical section? Just answer these questions. Can it possibly run in parallel? Can different threads run through it at the same time? Think of a driver. Of course it can happen. We can't say, hey, only one guy can access the disk or network at a time. Of course not. We have concurrency. Okay. Are you working on shared writable data? Yes or no? If the answer is yes, that's one more tick. It's looking like it's concurrent. Okay. If the answer is no, don't bother. Is at least one writer possible in that code path? If the answer to these three questions is yes, you are working on a critical section, you need to protect it. So guys, I made one small flowchart, but I think it's useful. If we keep this by our side when we are working on these things and we answer these questions and the answer is it is a critical section, then what next? Protect it. Protect it from what? From concurrent access. That's it. That's what we're talking about. Okay. Okay, fine. So guys, it's time for a quiz. Is this a concurrent? I mean, not concurrent. Is this a critical section? Can anyone answer? We have a global. It's being updated. Just look at the code carefully.
Yes.
No, it's not. You know why? You see that double underscore in it? It's a kernel module's init code path. It runs singly. It will never run in parallel. So see, the first of the questions is no. The first of the questions is no. So forget it. You don't have to worry. Okay. Now, what about this? This is part of a driver. We have a pointer to a global data structure. So think of that flowchart. It is a critical section. It's possibly concurrent. It's shared writable data, and it is being written too. So it is a critical section. We have to protect it. So if you write the code like this, you have a big fat bug waiting for you. Okay, that's all. Right? Guys, if we want to get more formal about this, we can. But I don't really want to go too much into formalities, but we can. So Marco Elver of Google made a presentation where he talked about this. In the Linux kernel, we have a formalized way of looking at memory. It's called the Linux kernel memory model, the LKMM. And the LKMM states, when do we have a data race? So see guys, among these 5 conditions written here, if the first 2 are true, then we have a conflicting access. If the first 4 are true, then we have a race candidate. And if the 5th is true, we have a data race. So this is a more formal way of saying, hey, do we have a data race or not? Now, this is fantastic. If we can literally say, check for this, now we have a data race. Then why don't we build a tool? that shows us, do we have a data race? Guys, it's been built. That tool is called KC-SAN, the kernel concurrency sanitizer. And I think Marco Elver is the maintainer. Okay, so use it. I have one slide on it. It's coming up. Okay, folks. So, you know that code path between T1 and T2, that's the critical section. So what do we need to ensure? We need to ensure it runs alone, serialized, and in some cases that it runs atomically. This word atomic is very important, guys. Atomic means run to completion without interruption. Okay, so especially in IRQ paths, it becomes necessary to have atomicity. So see, all these requirements start building up, because if you do it wrong, you end up with latent bugs. And you know, it might take a while for it to trigger, but it'll trigger one day, and then it's hard to debug. It's very hard to debug. Okay. So coming to atomicity, no, there are some misconceptions. The old misconception, which I think nowadays we don't have, we have a global variable G. If we do G++, is it atomic? So earlier, many of us would say, yes, of course it is. It's such a simple thing, but we know it's not. You have to do a load, you have to do the arithmetic, you have to write back the store. Now, that can take 3 machine instructions. It depends on 2 things. It depends on your machine, it depends on your compiler, which also means level of optimization. Okay, so see, guys, we want to write portable code. Don't make assumptions. Which compiler, which machine, which level of optimization, we don't know in advance. So do it the safe way. How? Using locking. Now, locking sounds like too much overhead for a G++, but there is an optimal way to do that locking. It's called atomic operators. So see, there are ways to do these things and optimally perform it, and it'll work. You can stop worrying about bugs. So execution of a single machine language instruction is guaranteed to be atomic. That we don't worry about. Single machine language. While a single machine language instruction is running, even if an interrupt comes, it won't get preempted. But after it runs, all bets are off. You can get preempted. Okay. Okay. Now, the next thing, processor word size accesses are atomic. We have all, I guess, been taught that this is the case. If you're on 64-bit and you're operating on 64-bit, it's atomic. 64-bit operating on 32, it's fine. 32 operating on 32, it's fine. But of course, on 32-bit operating on 64-bit is not fine. It will take 2 accesses. Okay. Now, you know what? The really interesting thing, Will Deacon is a kernel contributor, and he has literally proved that the second point is not necessarily true. Meaning, the only thing that's guaranteed to be atomic is a single machine language instruction. So guys, this is because of our modern machines and compilers. They are very highly optimizing. They can do out of order loads and stores. And we don't know what the hell will happen at runtime. Okay. Actually, the developer doesn't know how his code will run. We are in that state today. Okay, because they are so performant. But it can also bite us. So be careful. Okay. So what my whole point is, if you find this a critical section, protect it. Don't make assumptions. Okay. Okay. Here's that example, G++. Guys, have you seen this website? Okay. Very nice. Compiler Explorer. So I did G++ on ARM64 GCC 13, which is pretty recent. Okay. With optimization level 2, the optimization that the Linux kernel is compiled at. And look, G++ takes 4 machine instructions. Now, tell me here, can't we get preempted after 1 or 2 or 3 of them run? Of course we can. So don't make assumptions, guys. I keep telling people 2 golden rules. Don't make assumptions. Be empirical. Empirical means don't trust the book, the author, me. Try it yourself and see. KC-SAN. So guys, for my kernel debugging book, one of the topics is using KC-SAN. And here's a screenshot where it has got a data race. Okay, so see, all this tech is there in the Linux kernel and it's there for us to use. We usually don't turn these things on in production because there is a performance impact. But for your dev and testing, I always tell people, for God's sakes, have two kernels, a production kernel and a development kernel. In the development kernel, turn on all the debug features, run all your test cases with full code coverage. Only then the confidence rises that we are doing everything we can. Otherwise, we are, that fingers crossed kind of thing, okay, which is not good enough in production. Okay. Why do we have concurrency? Well, this slide is kind of obvious. SMP multi-core systems allow you to run in parallel on multiple cores. But it's also tricky. When I was younger, I thought that only SMP, then I have to worry. Well, nowadays, who has UP? Nobody has uniprocessor. But at least academically, even on uniprocessor, hardware interrupts cause concurrency. They cause races, because think about it. I'm working on a global struct. I'm updating it. An interrupt comes preempting me. In the interrupt handler, I'm working on the same struct. Don't we have a race? Yes, we have a race, and it's one processor, one core. There is still a possibility of a race. In user space, we have signaling, which will cause the same issue. Okay. If you're running in a critical section and you hit a blocking call, that means you schedule off the core, allowing another thread to come in. Isn't the data inconsistent? Won't we have bugs? Yeah. On 2.6, which is considered modern Linux, but now it's 20 years old, we can configure the kernel to be preemptible. Our Android phones are, most of our desktops are, some of our servers are, not all. So with the preemptible kernel, a code path in the kernel can get preempted at any time. Well, loosely speaking. So we don't know in advance. Now it's like user space. Okay, we can get preempted at any time. So how do we guarantee we are atomic? How do we guarantee we run to completion? Finishing our data update. Okay, so see guys, it's tricky, right? Now, by the time we reach here, you might say, oh my God, yeah, I chose the wrong line. Okay, but the good news is it's actually pretty easy to solve all these problems. We just use the appropriate locks. Okay. The difficulty isn't writing the code. It's in identifying the critical sections. Okay. You have to synchronize. Okay. What is a lock? So yeah, we want to do locking. So what is the whole promise over here? So see guys, we know these things. If we're accessing a global, I mean, multiple threads want to access a global. So A, B, and C come and they all want to work on it, but we can't let them. So what do? We take a lock. So the thread that gets the lock, let's say B is the winner. It sees the lock API as a non-blocking call. It goes into the critical section and runs. But the losers, they see the lock API as a blocking call. Well, loosely speaking, they have to wait. So whenever you wait, you're waiting on an event. What event? The unlock. So guys, the whole lock premise is we are guaranteed to get one winner. If n threads apply for a lock, you'll have one winner and n-1 losers. The losers will wait on the unlock. When the unlock happens, out of the n-1 losers, they will compete for the lock and one of them will get it. It will be the winner and you'll have n-2 losers. Now, that serializes, it makes parallelism, it defeats parallelism and makes it serial. Now, that's good, no? But what about performance? It's busted. It's terrible for performance. But guys, yeah.
Is there some way to prioritize the n-1 losers?
Yeah, use scheduling policy and priority.
Okay.
Yeah, Sched FIFO will always win in favor of Sched other. 99 is better than 90 priority. That's all. Yeah. So on paper, we say we don't know who will be the winner. And that is the way it should be. But if you need prioritization, do it. Use nice value, use policy, use real-time priority. The OS will honor that. It will honor that. Yes.
But there is always be a trade-off of using those policies. Of course, we get performance in one context,
Yes.
but it is not generalized that in other context we are lagging on performance because starvation, we are just allowing
Yes.
time others.
Yes, you're right, of course. So guys, it's all a balancing act, and that's where design is important, right? So just giving high priority to one thread or actually to many threads is not a great idea. Using the same priority level for multiple threads is creating ambiguity. So be careful. That's why we have 99 levels, right?
Additionally, also like even though you give assigned priority, it's not necessary that you can acquire the lock, right? So if
Yeah,
let's say
it's
somebody else has acquired the lock, so that is where the RT mutex came into play because it used to cause priority inversion, right? So it does not guarantee that even though you use priority scheduling, you will get the lock.
Correct.
You can attempt to get the lock by getting your time on CPU, but
Yes.
you get the lock
Yes.
is separate. Unless you support that scheduling in the locking also, till then you will not get the lock. Like it's not guaranteed rather.
No, see, guys, I should have said it. I am talking about vanilla Linux, not preempt RT or RTL. Okay. So if you configure the kernel as RTL, a lot of things are going to change, the things I'm talking about. And one of my last slides mentions that. Okay. I'm talking about vanilla Linux, which most of us work on. Okay. Not all of us. If you're flying a drone, you're probably using RTL. Okay. Anyway, let's move along. Folks, you've been to the airport, of course. On the 1 km from the airport, have you seen the toll booths? There are 16. I counted it one day. So why are there 16? Why not one? Can you imagine the traffic jam if there was one toll booth? That is what a lock is. Okay. So even civil engineers have common sense. And of course, being Bangalore, we still have jams. That's another story. We need more CPU cores. The road is the core. The threads are the cars and the bikes. It's a physical analogy. Have you seen a funnel? The mouth of the funnel is wide. The stem only allows one thread. So it's a lock. Okay. A traffic signal. So I was in Europe a few months back and the driver driving along says, "Oh my God, so many semaphore." So I was like, what? Then I realized, man, semaphore means traffic light. See how the word came about? Interesting, no? Okay, guys, this is just to show. 5 minutes. Oh my goodness, guys, I have to become performing. If you take a lock, it'll work. Guys, this is very important. Don't say I'm only reading. So there's no critical section. It's a very common mistake. Why? Because while you're reading, someone's writing. Then we get a dirty read or a torn read. Okay, it's a bug. If it's a critical section, protect it. Deadlock arises when you are using locks but don't do it right. So attempting to reacquire the same lock leads to self-deadlock because we have a golden rule. A thread can only acquire a lock in the unlock state. If you already have it locked and you're trying to get the lock, then you will wait for it to be unlocked. Then who will unlock it? No one. you're deadlocked. The more difficult case is circular deadlock, which is illustrated there. This is from my kernel programming book, guys. So, A and B simultaneously take two locks, A and B, but then each wants the other's lock. And that doesn't work out. They wait for each other forever. So that's called ABBA deadlock. This is a case of circular deadlock. You can have deadlock in a circle, A waiting on B, B waiting on C, C waiting on A. Now, guys, all this is like one terrible thing. How do I figure it out? So lock ordering is the most important rule. Document the order in which locks are to be taken and follow it. The Linux kernel people are quite informal. They don't write very big documents. They write documents because they're forced to. But it's in the code as a comment. So the order in which locks are to be taken, you must follow that order. Otherwise, they won't read your patch. Okay. Because you will cause deadlocks if you don't follow the order. It's the most important rule. Don't let starvation occur. Think about it. Use tools like perf to see where is the bottleneck. Use the flame graph. Keep the design as simple as you can. Okay, guys, I don't have time now. The spin lock is used for short critical sections because we wait by spinning. So we never context switch out. This gives us a performance advantage. So use it in those cases where you know the critical section is very short. But how short is short? We are talking sub-millisecond. Okay. Actually, the more important funda is the code in your critical section should never block or sleep. Then it's fine to use a spin lock. And in fact, you should. Okay. If you have code in the critical section that possibly sleeps, it hits a blocking call, and this is common, then use the mutex lock. So we can have longer critical sections. Everyone lives with it. It's okay. It's part of it. Guys, I'll show you in the next upcoming slides if they give me time. We have a superb feature from 6.5, the guard. With the guard, unlocking is done automatically. So you can say guard mutex, guard spin lock. There are slides which show you. Now that is a big thing because, like the leakage bug, it helps us in production. Maintainers will keep cursing people like me because we'll create bugs. Okay, so it helps. Okay, I talked about doing G++. Use atomic operators. The older one is called atomic type, but they are susceptible to bugs, integer overflow and UAF, use after free. The newer APIs are called refcount type. Use them. They are better. Guys, I've got slides showing a little bit on all these. Memory barriers are used to force a certain ordering of memory operations. Like writes or reads have to happen in a certain order. In some cases, it's very important. Like in DMA descriptor setup as a good example. Lock-free technologies allow you to do your critical section without taking locks. Now, that's amazing because it removes the performance problems of all these other ones. So how does it work? Per CPU is a great way at the expense of some RAM. The OS will make a duplicate copy of your data and each core will use that copy. So we are not racing with each other. We are working on our own copy of the data, so we don't need locking. I'll show you one practical use case.
But then in this case, uniprocessor kind of.
It doesn't apply. It doesn't apply. See, who uses uniprocessor? It would be very rare. It's for multi-core. RCU is one of the best. RCU, it'll take a little while to explain. It's in situations where you're accessing the data in a read fashion 90% of the time. It's called read mostly. or mostly read, then please use RCU, because the situation is very common in the Linux kernel. Okay, so looking up a path name, looking up a routing table, linked lists, arrays, radix trees, hash trees, it's extremely common to do it for read only most of the time. It's a lock-free way to do it. Okay, so guys, that is the that is the summary really. I don't think I have much time. So let me just take you to some summary page. Otherwise, they will kick me out. This is a nice example of per CPU, because this is the old way of doing it, using a spin lock to get RX processing done on the network path. But the modern way to do it is to use per CPU queues. So now there's no locking. There's no competition for a lock, and it becomes very fast. Guys, there are slides here on RCU, but I don't think I have time to go through all this. I can talk with you offline.
Talk to him in the hallway.
Yeah.
I know it's a big topic and it's not
Yes.
difficult to contain within half an hour.
Correct. Thank you. See, I'll show the summary table. You all can. So the summary table shows you when to use which technology. Does it disable preemption? Does it disable interrupts? Are blocking calls allowed? All that kind of stuff. Okay. So hope it's useful. Thank you, guys.
Any questions? Whatever problems we have, we want solution from him. Yeah.
Which is the guard API that you spoke about?
So we can do one thing.
I've seen it in the code base earlier, but I wasn't sure how it exactly works.
Right. Okay, it's not working with C-scope.
I think it might be a macro or something.
Yeah. Oh, I've made some mistake. No, there are instances of it being used. Peter Zylstra is the maintainer. I don't know a lot about how it works here. Okay. Here's what I remember. We leverage the cleanup attribute of the compiler to in effect call a destructor, which will perform the unlock. That is how they are doing it essentially.
Basically, I think it is, this idea is from C++ kind of.
Yeah.
So, resource acquisition, when you acquire, you have ref counts. And as the ref count becomes 0, then it's a free the resources. So that's the idea. They in compiler they optimize it, and you acquire the references, and you know basically there is a constructor and destructor concept, and as we are freeing it, a destructor is being called, and ref count is decreased, and once it is 0, it gets freed.
Thank you. It's fairly new, 6.5, and same for the mutex guys. It's both spinlock and mutex, and all variants of the spinlock.
Are they using only in drivers, or it's in common code?
Seems to be common code also.
It's
Co-card,
used in the
co-seed.
networking stack.
I think it's being used. Because see, once proven, we just get this benefit. It's like the dev-m KZL. Okay. Right? We don't have to worry about the free. It's very analogous. All those dev-m APIs. It's like that.
I think it could be in that path, file system path, where IOs, read-write IOs.
I'm sure it must be being used.
All devices have that. They use it in the newer version. In block devices, when they write to block devices, the drivers primarily
Drivers
use
basically
it.
primarily
There they
drive-
use it more. In the kernel, it's unnecessary rewrite in a larger sense. It's already been working. You are trying to rewrite something. It's wasted effort. Like it's already working. Why do you want to rewrite
I
it?
think for new development, they are.
Yeah, for new they would be
using-
using.
Guys, lot of bugs are leakage, resource leakage. So the guys have taken the effort to build this so that we start using it. Because we will reduce those bugs. Okay, so we should use those APIs. Because most of us do like driver kind of work. Or at least a lot of us.
Any other questions? Yeah, thanks, Kainwan. And
Thank you.
as I said before, it's a vast topic and yeah, we
Yeah.
can discuss offline. We'll meet again at 11:30 in the same room. So with the session from Sushant Rao on microphones.